Hello, everyone. I am Daniela Garcia, and welcome again to another edition of Encora Talks. Our topic for today is computational mathematics and applications. We have a great expert with us. His name is Victor Sanchez. Victor is a data scientist at Encora. He has worked on various multidisciplinary projects with experts in astrochemistry, biology, music, actuary, and insurance, in addition to having worked in the automotive and health sectors. He graduated with a mathematics degree from the Universidad de Guanajuato and specialized in statistics and sampling. He also received a master's degree in mathematical science at the Universidad Autónoma de Mexico, specializing in mathematical finance and fractional Brownian motion. Good morning, Victor. Welcome to Encora Talks. We are very happy to have you here.
Hi everyone, and thanks Danny and the Encoratalks team for having me. Good day, everyone. Um, like Danny said before, today I will talk about computational mathematics. The most basic use of mathematics in computer science is the use of logic gates, but that's not the only way of working. We have a large amount of applications in real life, um, like programming could be useful for solving mathematical problems. So we will talk about um, accuracy, efficiency, robustness, and stability of algorithms, among others. When we have a better mathematical understanding of the problem, this leads to innovate numerical techniques. Computer arithmetic and computational errors is used when the true value of a number is not stored exactly by computer representation. When you have coefficients that are obtained by imperfect real world measurements or system of linear equation, there are a classical problem, but going deeper, computationally there are lots of applications in which it is necessary to work with systems that have too many variables to solve manually. In addition to the implicit problems derived from working with coefficients that are too large or maybe too small or mixed. In a most basic level, talking about computational mathematics is moving real life problems that affect our daily lives to codes and algorithms and give them a look in a mathematical way. We could delve into the rest of the application of computing itself within mathematics. Let's talk about some of the theoretical aspects behind specific computational ideas, starting with machine learning. What is machine learning used for? Okay, machine learning allows a system to learn from data. When you provide a predictive model with data, you will receive a forecast based on the training data. Machine learning requires that the correct data set be applied to a learning process. We will focus on two approaches to machine learning: supervised and unsupervised learning, in which we have an idea of how the data is classified, and unsupervised learning, where the data is not labeled and we have an iterative process. Starting with the most famous problem. Linear regression is a technique used to describe a continuous response variable as a function of one or more predictor variables. The interesting part of here is that we can use it and apply it to several kind of problems to analyze experimental data, financial, biological data, and the parameters that define the line, here represented by the parameter beta, um, are obtained by minimizing the sum of the distance between each one of the points and the line. Okay, we can give a look to the last equation where we have a minus one. This minus one is the interesting part of the problem that refers to inverting the matrix obtained by this matrix multiplication. Inverting a matrix is a mathematical problem equivalent to solving a system of equations, something that I mentioned before, but there is not always easy to do. Computationally can be very complex, and even mathematically it could not make any sense or being impossible to solve this system of equations. This is derived from having semilinear rows, a phenomenon that can occur due to having variables overlay related predictors related to the system itself. And as I said, I mentioned it some slides ago. What does it mean? When you are trying to make a prediction to gross income or something like that, and your predictor variables are like number of males, number of females, and the total population, those are semi-correlated linear factors, and that's easy to see that if we add the number of male to the number of females, you get the total population. So you are using the same and the same again, and this can lead us um, to have an to have a matrix impossible to invert, and that's a really common problem uh, in computational mathematics. Okay. Here we have an example on a company which uses three different materials, and we are trying to determine which of these materials could lead to have defects on the company main product. Um, Using some linear regression, we are capable to determine that the material C in April 2020 is the one which causes the most of those defects, and that the most of them were detected on that specific month. So we are changing the presence of each one of the materials, and we can see that in that specific moment we have a big layer of defects. Okay. Here is another algorithm. This now talking about the unsupervised learning, K-means, which is a classification algorithm that groups objects into K groups or clusters. In this algorithm, we minimize the sum of distances between each object and the centroid of its group. The algorithm consists of three steps. First, we initialize the number of groups, and after that we choose those centroids. Okay, it can be chosen like randomly or following a specific schema according to our problem. After that, we will assign each of the data objects to all of the k groups, assigning them to its closest one. After that, we update the centroid, and we will update and update and update. It means we will repeat the steps 2 and 3, assign the points, and then update the centroid uh, until the new until the new centroid is stays frozen, in a way of saying, or it barely moves below a bandwidth which we feel comfortable with. Okay. Here's a really easy example where we can classify established industry leaders, mid-growth businesses, and maybe startups according to their sales and the years established. We can see those groups as green, red, blue. We can see that with more years and more sales, we can say that a new company can be classified as industry leaders. And the idea is really simple, since the algorithms um come from people idea and not only from black boxes. Okay. The support vector machine is a more natural way of splitting data into clusters. Thinking it in a three-dimensional space, we use a plane to split the data into two groups. But this idea could be generalized for several dimensions and several groups. Okay. As mentioned for the k-means algorithm, we will iterate and iterate until we have the best splitting as possible for support vector machine. But also both algorithms could present some computational errors due to outlier data. Okay, so for linear regression, sometimes we have the problem of uh, having matrices which could not be inverted. And here in the k-means and support vector machine, we can always have outlier data. What does it mean? That it is data that is not too close to the other data with the same classification. Okay. Now let's talk about some useful algorithms. Learning behind the idea of machine learning, starting with the LU decomposition, sorry, which was invented by Alan Turing in 1948, is when we factorize a matrix into two special matrices: L, a lower triangular matrix, and U, an upper one. We can see that in this specific kind of an LU decomposition, the diagonal, the main diagonal, is composed by only one numbers, but it's not always a rule for the LU decomposition. Okay. Um, sorry. The enormous advantage of having matrices with such characteristics is that the Euclidean distances and dot products are provided, which is very useful. For example, in recommendation algorithms. Another common application of the LUUL, the composition, is the bilateral user authentication. So that is something that we use day to day in cybersecurity. Okay. Um, we also have the Cholesky decomposition, which is a specific case to the LU decomposition, where we decompose a symmetric and positive definite matrix into a matrix and its transpose. Okay, we can see L to one, L to one. Okay, those are a matrix and its transpose. As the original matrix has those properties, the most natural way of applying Cholesky is in image processing. Okay, computer graphics, animation, computer vision, and among other image operation algorithms. We use Cholesky very deeply. Okay. We will move again, and now let's talk into some really specific, uh, a really specific application. All right. We will start with a biological model. Let's think on the variants of COVID-19 using the diagram here. We can think that a person has the initial variant. Okay. Each person that you infect can have the same variant, which we will call a clone variant, or develop a mutation from the person who infected him. For simplicity, we will consider that each person can only develop a single new variant. In visual terms, I'm having this graph here. For each node of our tree, only branches of the same color or clones, or only one type of clone can emerge. We will say that this process is subcritical. That is, that also for simplicity, we expect that the number of total infections will be at maximum of one. This is just for the simplicity of the model, but talking about this diagram in specific, we can think on the individual one, which infects the individuals 2 and 4 with the same exact variant, and then when the individual one infect the individual 6, the individual 6 get a new variant, and then the individual 6 can infect the individual 7 and 8 with that same variant, which is mutant, compared to the first one individual, and we can move on that. Okay, so we will think this like ignoring in certain way the pass of time, since here the time is like discrete. it's not a continuous time model. We can make it in that way, but it will be easier to follow about the maths itself. Okay. Um, okay, we will analyze these trees by sub branches of equal mutants, which we will call clusters. It means we will analyze the green tree, 1, 2, 4, 3 is one cluster. 6, 7, 8, 9, 10 is another cluster. Okay, we will call these clusters, and this is called allelic partition, analyzing um, each of the trees by sub branches of the same color, or it means at the same type of mutants. The number of infections will be a fixed distribution and independent of the other individuals because the process will be subcritical or almost critical. Each of the variants will eventually die out, and in particular, allelic clusters will be finite. What does it mean? That as we have seen, like in our daily life, the pandemics are not the same as when it started. Okay. Um, Getting a little bit technical on this, we will use some notation. The pair she, which is she c and she m, will be a pair of non-negative integer valued random variables, which is the number of mutant children's. I will switch between between children's and infected to get deeper into the Galton Watson um, names, correct names. It's just for the example. Okay. Um, I was in she C is the number of clone children's, and she M is the mutant children's. Okay. In the other side, she plus will be the total number of children's. Going back to the COVID example, will be the total number of people who is infected. Okay. Um, the notation at the end will allow you to indicate the probability that when counting the number of clone children of each element of our tree, we can think again of the green tree with n elements. K are the clones of their parents, and L is the number of mutated children, right? By defining the probabilities P0, P1, P2 as the probability of having zero children or one child or the two children, and also P, the probability of having a mutant child, and 1 minus P, the complement is the probability of having um, a clone child. So it doesn't look very clear, but it's K plus L on K. Um and in this way, we can see that this probability is really similar to the multivariate geometric distribution, and it's escalated by at the end using all the probability of having zero child, one child, two childs, and all of that. Okay. So after that, we will finish the notation um, with the noting and also adding the the trees image again to make this clear. We will denote by Sn plus the sequence of random variables that is obtained by subtracting the generation number n from the total population up to that moment in the tree. In turn, we will define Tn plus as the first moment in which the random variable Sn reaches a certain level. Okay. Um, mm, to finish with the notation, we will denote by Sn plus um, like mm, the walk itself when we are counting the number of elements. So we are trying to reach a certain level, okay? And AI, which we will mention later, will be the number of descendant mutant individuals of the eth ancestor, okay? Among other results, when we analyze the amounts previously expressed, we can express the joint probability for the first three and the number of descendant mutants for the first individual as just scaling by n the previous defined probability pi n minus k minus 1. Okay? What does that mean? That we have an explicit probability of how many infected people by the original virus will we have and how many of them will have the new variant. We just need to know how many vaccines will we need. Okay, so this example, this application is really useful for knowing, as I said, um, the number of vaccines needed for a population. Um, we can use some statistics to determine those those specific variables. I mean, we can calculate explicitly the probabilities p0, p1, p2 of having um, more or less people infected by each individual. Uh, as individuals are really large populations, um, it wouldn't be useful to make these estimations by our hand. So we need computer mathematics on doing this. And in this way, we can use computer mathematics and this specific model, allelic partition in branching processes proposed by Bertrand, um, for doing some estimations on how many vaccines will we have and for having some predictions on how long will the pandemics when a new pandemics appear how long will it last and things like that. So it is really useful using this model applied to epidemiology, but it is also widely used in predator prey models for some um, biological problems with controlling the population of some species and things like that. There are some variations of these branching processes, which is something that is really studied um, today, with some bottleneck bottles and some mixtures between them to have better approximations to real parameters, and then it can be used for making some predictions on the results. To be specific, like for knowing, as I said before, how long will the pandemics will last, and how many vaccines will we need, or talking about predator prey, if we need to protect any specific prey or something like that for having this equilibrium. Well, this is really used, and it's not only limited to biological processes. And that's it. Um, that's all for now. Thank you.
Thank you so much, Victor, for all the valuable information and knowledge you just have shared with us. We are now ready to start with our Q&A section. And the first question I have for you is LU the composition used for Spotify and other music streaming algorithms too, or just for video streaming?
Okay, it's widely known that Netflix use it a lot, since it's let us to determine in a easier way the
Mhm.
distance between, I mean, two directors or the distance between two actors and things like that. The same applies for two genders or for two specific songs. That's right. Um, but it's not limited to that. To that. Um, the question here is that all the streaming platforms for video or for music or for books or any others. I mean, for example, the Amazon recommendation system, they are not always the same. In fact, I
Mhm.
know that Netflix and also Spotify create some convocatories to some call to actions for new developers to send their proposals to new recommendation algorithms, because all we know that having better recommendation algorithms lets us to having more sales.
Understood. Thank you, Victor. The second question I have for you is the ChatGPT algorithm supervised or unsupervised?
Okay. Well, ChatGPT is an interesting model. It used supervised learning, but it also used reinforcement learning. So when you give it some answer, when it gives you an answer and you are not agree with that, you can give some feedback to ChatGPT, and that makes it like a reinforcement learning algorithm and not only supervised learning.
Thank you, Victor. The last question for today is allelic partition a method that is still in use for modeling populations, or is it old fashioned?
No, no, it is still news. There are some authors like Laura Catan from France. No, Bertrand itself is still publishing some papers and this. Here in Mexico, I know some people who work on branching processes, and also in Canada who works in branching and bottlenecks processes for modeling population dynamics. So it's really it's something that has a lot of material to work on.
Understood. Victor, thank you again. Thank you so much. And thank you everyone for joining us. Please keep an eye out for more webinars that we will be hosting soon. And we also invite you to watch the recorded webinars we have posted on talks.encora.com. Thank you so much.
Thank you. Bye.